only do that question 8 on page number 110 through 111. So let's go ahead and let's check that number 8. Alright, number 8, list the 4 main components of a heat pump. Alright, so the 4 main components are, you have refrigerant, you have a compressor, the condenser, and the evaporator. Of those 4, did you happen to notice which one's the most important? Refrigerant. But we'll talk about the reasons why for it later. Alright, so let's go ahead and let's think about your classwork. Alright, your classwork is from pages 99 to 105. You want to copy those bold terms and definitions 3 times each. So that'll help you as we're getting ready for tomorrow. That'll help you to review your terms and definitions. That'll help you to be ready for anything that may or may not happen tomorrow. So pages 99 through 105, all the bold terms and their definitions 3 times each. So it'll help you as you get ready for anything that may or may happen tomorrow. So go ahead and pause the video and then unpause it whenever you come back. Alright, I'm going to go ahead and I'm going to keep going. Alright, so thinking back over it to page 99. Alright, what do you call the changing from a solid to a liquid? Melting, good job. What do you call it if you're going from a liquid to a solid? Freezing, good job. What do you call the temperature whenever you have a substance melts? That's the melting point. What's the temperature whenever the substance freezes? Freezing point, good job. Typically it's the same number, like for water. It's still 0 degrees Celsius. I think I drew that too small. 0 degrees Celsius. It just depends on if you're adding or taking out energy. Alright, what do we call it whenever I throw in an object that'll dissolve into a fluid or into a liquid, technically? Alright, those are solutes. So what do we call it whenever, like for water, if I put salt or sand into it because I want to lower the freezing point? What do we call that? Freezing point depression, because it's getting lower. Alright, what do we call the type of heat? Like if you have a cup of ice, and so the ice cubes are melting on the inside. So it's absorbing energy, but the temperature is not changing. What do we call that? What type of heat? Latent heat, because it's there, it's just not showing up as the temperature change. Particular, what type of latent heat is it that's required a given mass of solid into a liquid? So it's going from a solid to a liquid. What do we call that? What type of latent heat specifically? Heat of fusion. Now we use the words heat of fusion. Technically, if you're going from a solid to a liquid, it's heat of fusion. Technically, if you're going backwards, it's heat of crystallization. But your book and scientists understand if you say heat of fusion, it's the same amount, just depends on what direction you're going. But technically, it has to do with a solid turning into a liquid. Alright. What do we call the change from a substance from a liquid into a gas? Evaporation. What do we call it if it's the reverse? If you're going from a gas to a liquid? Condensation, good job. There are 5 things that affect the rate of evaporation. So, drawing my cup again. That's a decent cup. So, the rate of evaporation. What are 5 things that affect it? Name as many as you can. Temperature, surface area, strength of the air currents, the air pressure, and the properties of the liquid. So, note those 5 things. Alright, what do you call a solute that I throw into a liquid and it doesn't evaporate easily? Like what do we call it whenever you have a property that doesn't evaporate? Like some liquids, they just don't evaporate easily. Non-volatile. What if they do evaporate quickly or they evaporate easily? Volatile. So maybe none of that. So liquids that evaporate rapidly are volatile. Liquids that evaporate slowly are non-volatile. Alright, what do we call it whenever it's not just evaporation at the top, it's evaporation is occurring all throughout my liquid? What do we call it at that point? We say the liquid's what? Boiling. Good job. What do we call that point or that temperature whenever it starts to boil? Boiling point. Good job. Alright, there's several things we can do to raise the boiling point. So if I take my cup of boiling water and I go up to the top of Mount Everest, will it boil more or boil less? Why? Well, hopefully you said it'll boil more because there's less pressure, so more water can escape out. What if I take this to the Dead Sea? Will it boil more or boil less? Boil less because there's more pressure pushing down onto it. Alright, so that's called boiling point. Oh, what do we, if I take a non-volatile solute and I throw it into my liquid, will it raise or lower the boiling point? If there's something like salt cluttering up the water, it'll raise it. So what do we call it whenever you raise the temperature that way? We'll raise the temperature at which water boils that way, particular. Boiling point elevation, good job. Alright, what do we call the amount of heat required to have your individual grams of water have enough energy to turn into water vapor? What do we call that? Heat of vaporization, good job. Remember, that's also a type of latent heat or hidden heat because it's changing those bonds, how they are. So that's heat of vaporization. If you're going backwards again, it should be heat of condensation, but again, scientists, they use the term heat of vaporization for both ways for it. Alright. Okay, I think that's where we left off. So hopefully you didn't spend on your classwork. It's only going to take you about 10, maybe 15 minutes tops. But make sure that you are using your classwork well, so that way you're studying during our 15-minute class period and not just trying to do it after class or before class. Alright, so vapor pressure is the next major thing we got to talk about. So whenever you have evaporation and condensation occurring, typically one is stronger than the other at a given temperature. So whenever you have, like on a hot day, typically evaporation is faster than condensation. You might have some of your individual gas molecules lose energy and condense back down, but typically on a hot day, evaporation occurs faster. That's how come you'll have a puddle evaporate on the sidewalk. In some cases, you'll have them be perfectly equal. So, the rates of evaporation and condensation are affected by pressure the vapor exerts on the liquid and by temperature. So, it's talking about if evaporation occurs faster, then the vapor that's hovering right above the liquid, it can contribute as extra pressure on the liquid. So your book points out that if condensation occurs more quickly, the overall effect will be condensation. The rates of evaporation and condensation are affected by pressure the vapor exerts on the liquid and by temperature. So if it's dry outside, a lot of that water vapor wants to escape and wants to move away, far away from it. If there's a lot of water in the air, then the water won't evaporate as easily. And so because of that, there's a higher vapor pressure, or the water's kind of just, the evaporated water is kind of just hovering. And so because of that, it's contributing and adding in extra pressure. That's probably the reason why down here in the South, whenever you sweat, the sweat kind of just stays on you and you just feel gross and nasty. But if you go to Arizona or somewhere like that where it's drier, the sweat will evaporate off you faster because there's less molecules of water in the air to begin with. Alright, your book points out though that sometimes you will have a state of equilibrium where the water evaporating and the water condensing are at an equal rate. We call this vapor pressure. So flip over to the next page. This is whenever you have evaporation and condensation occur at the same rate at a given temperature. This is called the vapor pressure for that temperature. It does vary from temperature to temperature, but it's talking about, okay, here's the vapor pressures of water for it. Now keep in mind it's showing you, okay, here's the differences of water at different degrees Celsius. So you have the vapor pressure listed up here, and so this is really cold, almost freezing, so for the vapor pressure. So there's not, so your book points out there's not a lot of vapor pressure for this one. There's not a lot of pressure on it because typically there's not a lot of pressure just because they are so cold and they don't want to evaporate. At this temperature, they want to be more of as a liquid, so they're having to treat them specially for it. If you have 100 degrees Celsius, you'll notice this is the pressure of our atmosphere. This is the normal vapor pressure for it. This is whenever it wants to turn into that gas. If you increase it a lot, the vapor pressure has to increase a lot. So that's part of the reason why that the vapor pressure for this one, you have to take off the pressure so much, because if it has this amount of, if it has this low of an energy, it doesn't have enough energy for it to turn into a gas. That's why they had to basically suck out so much of the pressure, remove so much of the gas, and keep it in a special container. Because remember, at 0.0 degrees Celsius, what state does it want to be in? Typically, it wants to be freezing into a solid at that point. So they had to pull out so much pressure, so that way, even though it's super, super, super cold, they're making it exist in the gaseous form. This is why we don't see this typically, because of our atmospheric pressure. We don't see it go into the gaseous form like this at this temperature. This is what our normal atmosphere is. So whenever you have 100 degrees Celsius, that's whenever it has enough energy to go ahead and turn into a gas at normal atmosphere. And then, if you increase the pressure a whole lot, you have to give it a lot of energy for it to turn into a gas at that point, because it has to overcome all that pressure. So that's what it's talking about with vapor pressure. This is whenever the rates of evaporation and condensation are equal. This is whenever you start to notice it. We would say it's starting to boil. So that's whenever we would start to notice it. Alright, so make a note, the temperature of the liquid increases, the vapor pressure also increases. The temperature which the vapor pressure equals the pressure of the air above it, that's the boiling point. So again, that's the reason why if you take away pressure, the boiling point goes down, because it can boil at a lower temperature because there's less pressure pushing on it. If you keep it at normal atmosphere, it'll boil at what we say is the normal temperature. But then if you increase the pressure, you have to give it a lot more energy for it to overcome all that pressure and for it to go ahead and boil out. Let's see, your book points out as well, the vapor pressure equals the pressure needed to keep a liquid from boiling at a given point. So, your book points out in a couple different situations talking about this again, but that's probably the reason why they have to keep them in special containers, is because they're changing the temperatures so much, or if you want to put them in these pressures first, you have to take out so much energy for it. Your book points out at a temperature of 0.01 degrees Celsius, only 0.6117 kilopascals of pressure are needed to keep the water from boiling. But, let's see, I lost my spot, I'm sorry. The liquid water in an airtight container at 0.01 degrees Celsius will boil only until the actual pressure of the vapor in the jar equals 0.6117 kilopascals. So that's what it's showing you, that if you want it to be a gas at this temperature, you have to suck out that much pressure. So it's a little bit confusing over how they're showing it, but basically, if you have a container and you seal it, I'm going to use this one, and you seal it in an airtight container, if you want it to be at a gaseous state, since the air pressure typically is what's pushing on it down to keep it from evaporating, that you have to basically remove some of that air pressure if you want it to be a gas at a lower temperature. So for it to boil at 0.0 degrees Celsius, you have to pull out most of the pressure, so that way the water can go ahead and change into that higher state. If you want it to boil at normal temperature, you have to put it like normal atmosphere, but if you want it to boil at a higher temperature like a pressure cooker, you have to get it much more energy. Alright, that's the basic ideas for it. So your book, wrong direction. Thought I had the diagram. Full of other substances. I guess not. Alright, so vapor pressure of the vapor pressure of selected liquids. So your book points out in some cases the vapor pressure, remember this is whenever the vapor pressure equals the pressure of the atmosphere. So make a note of that on page 106. The temperature at which the vapor pressure equals the pressure of the atmosphere, that's the boiling point. So once you have vapor pressure equal the atmospheric pressure, that's whenever your water now has enough energy, or this liquid has enough energy to go ahead and to boil and to evaporate. Your book gives you several pictures at the top of page 107 showing you for ethanol, diethanol ether, and isobutane. Just showing you how these will boil at 25 degrees Celsius, at 25 degrees Celsius, they will boil because of those different temperatures. So, the vapor pressure for ethanol is 7.86, I cannot read this far away, 7.863 kilopascals. Vapor pressure of diethyl ether is 66.91 kilopascals, and the vapor pressure of isobutane 350 kilopascals. You don't have to know them. It's just telling you that's the vapor pressure. If you get that pressure to equal the atmospheric pressure, that's whenever they will start to boil. Alright, so let's look down on page 107 with the isobutane. So your book tries to give you this diagram showing you how some substances, they exist as a gas at room temperature because their vapor pressure is larger than the atmospheric pressure. And so because of that, they have a tendency to boil at room temperature. So let's read about isobutane. It gives you this diagram, and I have a moving diagram for it. Alright, isobutane, or C4H10, is a flammable liquid and has a vapor pressure considerably greater than that of water at standard atmospheric pressure. A pressure of at least 321 kilopascals is required to keep the isobutane a liquid at room temperature. Because of its high vapor pressure, isobutane is used in aerosol products to maintain pressure in the can even after some of the product is used. The pressure within the can contains isobutane can never remain below 321 kilopascals at room temperature because any drop in pressure instantly causes more isobutane to evaporate, restoring the pressure. When the spray nozzle is depressed, a mixture of isobutane, which is forced down the nozzle by the pressure within the can. Because isobutane is extremely flammable, one should never spray hairspray or any other aerosol near flamer matches. Alright, so what's it saying? Alright, your book points out that this one, it has a vapor pressure much greater than water. So its vapor pressure, I thought I saw it, 321 kilopascals. So that's the vapor pressure for it. So it is much higher than regular waters at room temperature. Remember, water boils at 100 degrees Celsius, or water will start to boil at rather atmospheric pressure at 101 kilopascals. This one requires a lot more pressure. So because of this one, it has a lot more vapor pressure, so it wants to go ahead and turn into that gas because its vapor pressure is so much stronger because it wants to go ahead and be in that gaseous form. So because of that, you have to keep the pressure on the inside of the can. If you want it to stay in that liquid can, you have to have 321 kilopascals for it to stay in that liquid portion for it. So whenever you use a can of hairspray, and they're using isobutane as an example, whenever you use it, because you're opening up the inside of it, some of the gas will start to escape out. But once you lower that pressure just a little bit, then since you've lowered the pressure on the inside of the container, some of it already goes and evaporates because since the pressure is less, it wants to go ahead and go into that gaseous state. And so because of that, since the overpressure is released, some of them can escape and turn into a gas now. So it's constantly at that 321 kilopascals of pressure on the inside. Even if some of them escape, some of the liquid will evaporate and turn into the gaseous form. So that way it's at that constant pressure over and over and over and over again. So that way your aerosol can still has that fine mist, and that's what's causing it to work properly. Your book points out some campfire starters and pocket lighters also use isobutane as a fuel. When the valve is open, isobutane and vapors are forced out through the valve by the vapor pressure of the isoprene in the reserve. A spark ignites, escaping the gas, forming a flame. Just telling you how this works. You don't have to know how it works, but your book's just pointing out that's the reason why some substances just exist at room temperature as a gas, like isobutane or like nitrogen. It exists in the air as a gas. That's going to have to bring it to a really cold temperature or keep it under a lot of pressure if you want it to be in a liquid at room temperature. Alright, so that is pretty much it for vapor pressure. Oh, let's talk about critical temperature really quick. So your book points out, in some cases though, if you keep adding in so much heat, it doesn't matter how much pressure you put on it. So above a certain temperature, a substance will start going into the gaseous stage. It doesn't matter how much pressure you push on it, how much you try to press it to keep it as a liquid. Once you get that certain temperature, it'll automatically go into the gaseous stage. It doesn't matter how much you're trying to press it down. It has so much energy that the gas molecules can't stay together. They have to split apart at that point. We call this the critical temperature. So above this temperature, critical temperature, your book says water. So your book points out your book points out that this is just for water in particular, but this works with almost any type of liquid, so a substance. But your book points out water specifically. It cannot exist in the liquid state of the hazy gas regardless of the pressure upon it. That's whenever it has so much energy it can't stay in that liquid state anymore. It has to convert into the gas. Alright, I believe that is everything about vapor pressure and about critical temperature. So we're going to go on and we're going to talk about the heat pumps. Alright, so looking on the next page, talking about a heat pump. That heat flows from an area of higher temperature to lower temperature. We've already talked about that, how heat only flows in one direction. But you can't force it to go backwards. Now remember, you can decide I'm going to use energy and force it to go back the opposite direction. So a heat pump is a device that can use mechanical energy and latent heat to transfer thermal energy from a colder location to a warmer location. We find these in some of our central heating refrigerators, or in your refrigerator, or maybe in your air conditioner in your car. So your book points out a heat pump. This is a device to use mechanical energy and latent heat to transfer thermal energy from a colder location to a warmer location. Alright, lots of terms there that you should recognize. Alright, mechanical energy, so that's energy you get from motion. Latent heat, remember that's the hidden heat to where you don't see a temperature change, but it's going from one state to another. Transfer thermal energy. Remember that's the energy or heat energy of the molecule. So transfer thermal energy from a colder location to a warmer location. Alright, so how does this work? So going back over to my slide for this one. So your book uses this picture and then it uses another diagram a little bit later on. I'll hop back and forth between them. Oops. Okay, I'm going to move this because it says it's about to die, so I'm going to plug this in really quick. it's how a heat pump works. It actually works out really well, and it's kind of an ingenious design over how they designed it to work. Alright, so Dr. John Gorey, he was a Florida physician. He wanted to come up with a better way to help keep patients' rooms cool. So he wanted to produce ice blocks to cool the hospital room. So he wanted to come up what would be something to be, so that way I can have a cooler temperature for my patients. Let's see, I lost my spot, I'm sorry. So that's the reason why he wanted to do it, was so that way he could cool down the room for his patients in particular. So we use a little bit of a different design today, but it's the same basic idea. So your book has this picture on page 109, but your book has a better diagram showing how it works on page 108, so I'll flip back to that one in a minute. So your book points out there are 4 basic parts for it, and there's a high pressure region and a lower pressure region. So the major component is the refrigerant. Make a note for that one. That's the most important component of the heat pump. Now, most refrigerants have boiling points considerably lower than the freezing point of water. That for this one, it wants to be in the gaseous state at a regular room temperature. So, most of them are liquids with boiling points considerably below the freezing point of water to where they will evaporate at a normal temperature for us. To begin this cycle, the compressor compresses the gaseous refrigerants to a very high pressure. Now, if I take a gas and I condense it to a really high pressure, not only will it be underneath so much pressure that it'll build up a lot of heat for it, according to Montan's law. Remember, thinking back for Montan's law, you have P1 over P1 equals P2 V2. Nope. P2. That if you have that high increase of temperature, you're going to have that high increase in pressure. So that's what they're doing. Is this first one, this compressor, they are forcing it to have a super high temperature because they're forcing all the gas molecules together. And the gas molecules, they don't want that. So to begin the refrigerant cycle, a compressor compresses the gases, and so it causes the temperature in this section to rise because all of it is being forced together. That's what comes typically at the bottom of your fridge. Your condenser, you might feel some hot heat coming out the bottom of it if you put your hand or your foot against the bottom of a fridge. And again, there's different models. But that's probably the reason why it might feel like warm air is coming out from underneath the refrigerator, because the compressor is taking the gaseous form and is pushing it tight together. And they don't like it, so they're giving off a lot of heat. So that's the compressor. Let's see, your book points out as well that the compressor is often driven by an electric motor that's from your refrigerator and needs to be plugged in. And if the power goes out, your refrigerator starts working because your compressor uses electricity to force that gas together. Alright, your book points out the hot pressurized refrigerant passes through a radiator called a condenser. This allows it to cool down to room temperature. So, going through the compressor, it goes through the condenser down here in this section. This is whenever it cools to room temperature at this point. As it is condensing though, it's giving off its latent heat, and that's why it also feels warm as well. So you have a compressor down here, you have the condenser that allows it to cool down. So as it goes from that gas into the liquid stage, it's giving off heat because it's losing heat from the gaseous stage because it's going from a gas to a liquid. It's giving off or losing heat. So that's why you'll typically feel it down there as well. Not only just because it has a lot of heat, but it's giving off that heat now because it's going back down. And that's what it's talking about. The condenser feels very warm to the touch because it's giving off. That's the reason why you feel it typically is warm air down there. So the compressor forces them together, giving them a really high temperature, and then they'll give off that air as they condense back down or go back into a liquid. Now, because your cold air has to be up at the top of the fridge, that's why the model is designed this way. So the next section is it'll go to the evaporator. So you have, so passing through the evaporator, it has a very small hole, but then once it goes through that, it allows the pressure to drop. Now, once the pressure drops, that means you can have your liquid go back into the gas again. So whenever it does that, it goes from being into a liquid into the gas. So it has energy, but that's because there's less pressure above it. So once it turns into that gaseous portion, when it turns into that gaseous portion, it has to absorb a lot of the air from around it. So, because of that, some of the liquid changes instantly into the vapor and absorbs a lot of the thermal energy, and it cools drastically the air around it. So, the gas molecules themselves have absorbed energy, but since they're absorbing it from the air around them, they've absorbed a lot of that energy, so it cools a lot of the air around them. So, don't think about, okay, What's happening to the individual gas molecules? It's the air around it that it's affecting as well. So as you have this cool mixture absorb thermal energy from the air, the remaining liquid refrigerant boils and turns into a vapor as well. So once you have some of it, instantly changes over and absorbs energy. So once you have the others, they can also, as they evaporate and absorb that energy as well, because they're absorbing it to turn back into that gaseous form, they're cooling the air around them. So again, they go down here and they start this process all over again. So your book has this model, kind of help explaining it. I like this model, so I'm going to go over to it. I moved it around, I'm sorry. Oh, where is it? Hang on. Sorry about that. I lost it. I thought I had them all. Oh, there it is. Found it. Alright. Showing you for this one, here's the 4 parts again. So again, this is the high pressure region. Where's my mouse? High pressure region on this side. You have on this side the low pressure region. So heat heat flows from the condenser to the outside because it's underneath such high pressure, raises the temperature of the overall gases, so they're giving off some of that energy around them. So that's the colors it's in with the orange colors because the heat is being given off from it, because they're forced together, so close together. It goes through the small opening, the evaporator. So it absorbs heat from the air around them, because it's going from a liquid back to the gas. And then it goes through and it does it all over again. So that's what it's showing you in that section. That it goes from being a liquid to a gas, and it does it partially because of the pressure on this side. And then over here, because of the dropper pressure, it jumps back to being a gas, but it absorbs the heat from the air. So because of that, it makes the air around it really, really, really cold. That's how come the refrigerant is the most important part, because it's that one that's causing it to either give off heat or to absorb the heat and to make the air colder around it. Alright, so that's what's happening on page 108 with this refrigerant. Your book points out how this also works with the ideas of a refrigerator, and how it works out with a heat pump as well, if you're talking about a heating unit. I think I'm going to go ahead and stop there though, so that way, because you had classwork and you were working on stuff, I don't want to overwhelm you. So don't forget though that the background paper is coming up. So make sure though that make sure you work on that to the final draft. If you have any questions about it, be sure to email me. Alright, I'll go ahead and I'll give you your homework though. We'll finish talking about this with refrigerators tomorrow. Sorry, I just noticed the time. Alright, your homework for tonight. Read pages number, where am I? Read pages 108 through 110. You notice we're almost finished with the section, so we're almost finished with the chapters, so that we will finish up the material tomorrow. Start reviewing on Monday for your exam. So read pages 108 through 110. Answer on page 111, the section review 5.4, questions 9, 10, and think number 2. So on page 111, the section review 5.4, questions 9, 10, and think number 2. You want to go ahead and start studying though for anything tomorrow, but then also you want to start studying for your exam coming up next week. Alright, so a little bit shorter lesson today, so be sure to review over this, know your terms and definitions, and so keep working on it and keep studying on your own. Alright, you have a great day.